Good afternoon.
Oh, really?
I'm curious, why do you show the classroom every time?
Oh, because I thought you guys like to talk to each other. I suppose
Oh
that was.
yeah, no, it's fine. I was just curious if like you were obligated to or not, so I was
No, no,
curious.
no, 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 no.
Okay.
This is a camera option, right? I don't think there's any rule for this. I
Okay.
just usually you guys come and probably talk to each other.
That's
So,
very nice of you. Very considerate.
but now there is no one, so I'm just setting up the camera at this point.
Yeah, no, I understand. I understood you were set up the camera, but I did notice you do that when nobody's here every single time. Like you check the range of motion.
Oh, yes, that's correct.
So that's why I was curious if it was an obligation since you're recording, like for someone in the department to look
No,
at
no,
it or not.
pretty much. Yeah, there is no. In fact, probably this is not official. I think if you go by the university, I think they might want not to record because there is a lot of privacy issues that comes in with recording. Right?
Understood.
So that's why I think I wrote on my syllabus that this is going to be recorded and such a thing. So what I do is that I do record it, but then I don't make it public. If you notice, even if you subscribe to this channel, you won't get any information about this recording.
Okay, interesting.
So you just make it unlisted in that option. So to a certain extent, it's private, but still it is out there on the internet. So in that sense,
Right. As long as we don't say our location, names, or anything like that, right?
So yeah, so at a university level, they have to be careful. That's what I'm trying to say. That so
Yeah, I understand.
so it's tricky. Yeah.
Well, I subscribe to your YouTube channel, so you at least have one subscriber.
Yeah. So do you get any information whenever the video gets posted? Probably not, right?
So I didn't click alarm or notification or anything, but I see that you have a new video posted on your channel.
Yes, that's correct. Yeah, even if you say yes to the notification, probably you won't get it. That's all. Yeah, that's what it means by unlisted. Which
Okay.
means that if you search for this video on Google, you won't find it. That's
Okay.
all. But if you give a link to someone, you will find it. So
Understood.
it's not private. It's not public. So hopefully during these times they will people don't mind this much, especially the students. And as I said, privacy is also an issue. Okay. As of now, I've not got in trouble. But anytime anyone says the point is, I'll just stop recording. That's it. You cannot have both, right? You can have recording and not post it.
Yeah. You could. It'd be just very, I guess, not productive. I mean, you could go over what you said, so that way you could guarantee, like, nope, I said it. It's on the test. I said it once.
Yeah, I wrote it on the syllabus, so that's just so that everyone knows. But I assume that if we are coming online and attending the classes, the expectation is that you would like to refer to this. That it helps, I suppose. But in case anyone has.
No, I really like it. Because there were times in my previous classes with you that I do wish I could have listened to the lecture again, because I'm like, you explained it so clearly and my notes are not very clear. What happened? And so I'm thankful for the recordings.
Yeah, I think it should be helpful. Yeah, I do feel so. Oh, so now when the students did come, you did not get to see them. Here.
Hi, I'm waving.
Okay, so I think some of us are here. Curtis, Matt, and who's missing? Travis. How is everything? the semester catching up? Getting this done. You have homework 2 due August 31st, that's Monday. Homework 3 is not due, but it's relevant. Remember, content is necessary. There might be a question from it, like homework 4 is going to be due. So even though this is due Monday, one would expect it to be next 1 week from then. I made it a little shorter duration, so it's due September 4th. Friday. Next week you have 2 homework, but hopefully it won't be bad. And I primarily did it so that I can squeeze it one more homework in between before the exam. September 11th, it's a Friday, and that's the day of the exam also. We will have a homework due on the day of the exam. Seems like I'm pushing on it, but let me know if you guys really think this is too much. I shouldn't be doing this. Then I'll reconsider something. No one wants to say anything, so I assume that's okay. Okay. We introduced the idea of working on vector algebra using the gradient operator. So that was primary most of what we did in the last 2 weeks. I think this is the second week. And one of the things we did notice, let me write this more explicitly. Let's say electric field due to a point charge. You should be knowing this from some introductory physics course. So electric field due to a point charge. Let's also say it is at the origin. I don't have to place it at the origin, but if I place it at the origin, it's a small simplification. This is, in general, this could depend on time also, but I'm saying is just stationary at the origin, so there's no time dependence. This is equal to, in SI units, we'll work in SI units all through, 4 pi epsilon naught times Q over R squared. And what is epsilon naught? Permittivity of vacuum. Any numbers?
Very small.
Very small, that's correct. Relative to something, right? That's usually, just to be critical, very small is very relative, unless you give another number. For example, in SI units, this is equal to 1, right? So yeah, so good point. So it's 8.9, I think. Right? I think it's 8.88, 8.9. Is that right? Into 10 raised to minus numbers 12 times 12. Is that correct? Right? You guys just accepted. Right. What about the units?
1 over length squared.
1 over length square. Why do you say that?
That's not true. No.
Where from here?
There are no units.
Why do you say that?
I don't know. I don't remember what the units of electric field are now. Charge per distance.
If you multiply by charge, that becomes a force. Right? Force, remember, is charge times electric field. And the dimension of force is known. You should be knowing it. So what's the dimension of epsilon naught?
Newton is what, kg meter per second squared?
I'll just say 9 Newton is good enough. Yeah. So, or I should, yeah, I was asking you dimension. How about units? Then you can use any fancy unit. So Newton, this is Newton per coulomb, meter square coulomb, right? So it'll be Newton meter square over coulomb square. That's good enough. And if you want dimensions, then you convert the thing. Because I cannot leave that as a number alone, right? I have to put the dimensions in there. And this is permittivity of vacuum. Of vacuum. What is the physics of epsilon naught? What does that mean? What do you mean by permittivity of vacuum? Again, in very simple words, every material has an electrical property to it. That means to say that how much can you polarize something? If you have a material, it has charges, plus, minus, plus, minus, how much? Three charges, right? If I were to put an electric field on this, usually the positive charges get towards the, so they will all move in this way, right? So there are 3 earlier, so this is positive and negative. Often, this is, if it was a perfect conductor, they will go all the way to the surface. Sometimes they're not free to go, they can only go a little bit, or sometimes they only can move around. So usually the diagram that you suggest is that the positive, negative, these are atoms, negative, positive. So they all tend to orient themselves with the electric field, but now they're not very free to do that. For example, if it's a perfect insulator, you cannot just do it. Right? It doesn't do it all. So how much can it do is the property of the material, and in that sense, this is the property of vacuum. And we would think that vacuum should not be able to do any polarization at all, but this is the limit in that sense. So imagine if vacuum also could be polarized, and it can be in the sense there is a positive and matter and antimatter have negative and positive charges. In that sense, that's the way to imagine that. But it is also the perfect insulator. So vacuum is your perfect insulator. If you stretch your epsilon to all the way to large values, that's infinity. And on the bottom side, this is epsilon naught. That's the 2 extreme values it can take. And the bottom value is epsilon naught. So this will be an insulator that will be a conductor. So it's convenient to say that epsilon over epsilon naught is what is the physical quantity. Then it becomes dimensionless quantity. This is the property of a material which tells you how good a conductor this is. Is this insulator or conductor? So this is insulator, perfect insulator. And that's a perfect conductor. And we will see that there is much more, or I don't know how much, as you learn more and more, you notice that there is a pretty good complicated structure in this. This is oversimplified version of the idea of an insulator and a conductor. So that's the idea in this. So that I just wanted to say what is that epsilon naught. As of now, we will not get into the physics of this. Charge Q will be measured in coulombs. 3 kinds of charges, right? Positive, negative, or neutral. That's all it is. What's missing in this equation? Direction. Very good, right? So this has to be a vector, right? It has to be a vector on the right hand side. That is r hat. If it is a vector on the left, it has to be a vector on the right. This is the electric field due to a point charge at the origin. If it is not at the origin, what changes? Don't place it at the origin, what will change?
You have to have like a difference vector, a the magnitude.
Exactly. So this is at the origin. If it was not at the origin, I'm going to move it. So this will be 1 over 4 pi epsilon naught. This will be r minus r naught. This is the position of the charge. Right. Then this also changes. This r hat is with respect to the origin. So what you typically do is, instead of saying this is r minus r naught divided by magnitude of r minus r naught. So often you write r minus r naught divided by r minus r naught cube. That's your electric field if it is not at the origin. Again, we'll come back to this as we proceed. But as of now, I just want to use this equation. Okay. Any questions at this stage? This should be familiar. Maybe I just wrote it in some vector form. So, okay. I erase this part. Is it?
The top part of the fraction is just 1.
That's correct. This is 1. Oh, yeah. This is 1. Yeah. What is? Yeah, I erased it. Right. That's 1. Yeah. Huh?
It's not cube.
Oh, there is cube. Sorry.
Professor, is the units actually reversed? Is it coulombs squared per Newton meter squared?
Very good. Very good. That's correct. That's very good. Yeah, good catch. And no one caught that. Yeah. How did you figure that out? You just checked on me, huh?
The distance, it gets weaker at a longer range, so it doesn't make sense to be stronger at a longer range.
Yeah. So this is good catch. Because this is the inverse of this, that is Newton meter squared. So sorry. Yeah. Good catch. Yeah, thank you. Thank you very much. Okay. Any other comments, questions? Okay, so that was just so that I can use that expression. Let me get into that now. We'll come back to this. Okay, and I can erase this. Okay, so that's the electric field due to a point charge, and we showed we did not use this 4 pi epsilon naught, but if you were to evaluate the divergence of this electric field, what will you get? Right, we did this a couple of times already.
0.
Except at the origin. So this is equal to 0 right? If r is not equal to 0. Except that's 1 point. Very sensitive thing to say, that 0 everywhere except at 1 point. And then immediately the question comes, oh, what about that point? Or what is it equal to? So let me not say anything there, but instead we also know that if I were to do this integration, and we did this, if I were to do this integral, and let's say on a sphere, so the volume we integrate is over a sphere of radius r. Right? How much do you get when you do that? Charge inside, and since there is an epsilon naught, that also survives, right? So we did this without these units, and we got a 4 pi. The 4 pi cancels, and then q over epsilon naught comes out. That's a constant, right? Whatever that constant is, if you know the charge, it's some value, right? If this was 1 coulomb of charge, that's some value. How about 1 coulomb of charge? How much is that? Is it big charge, small charge?
I think it's fairly reasonable compared to an electron, right? Doesn't an electron have...
Electron is 10 raised to minus 19 coulomb, yes. But suppose you have We have 1 coulomb of charge here in this room.
Probably not a lot.
It's too big actually.
Oh, is it?
Yeah, 1 coulomb of charge is too big. It's too strong. A micro coulomb is good. If it is 1 coulomb, probably we are in danger. Probably, right? I think things will collapse. I think again, yeah, extra credit, right? Yeah, so extra credit is the following. Extra credit, right? How do I state this?
How dangerous is 1 coulomb?
Yeah, but that's a little vague, right? What do you mean by danger?
I mean, like less than 1 amp would kill you, and that's just a coulomb per second. Right?
1 what?
Less than 1 amp can kill you. Right?
Yeah, no, that's not what I meant by danger. Yeah, so that's where the question comes now. Yeah, because in current there is a danger in the sense it can cause you death, right? What I was saying, let's say,
Like like
yeah,
actually repelling objects in the room.
yeah, exactly. How much charge do you? Okay, here's a specific problem, right? Let's take 1 centimeter of. This is not really dangerous, but let's say this is 1 centimeter metallic sphere. So this is a sphere, metallic sphere, let's say. And now we place a charge on this. And let's say we place an amount Q charge on it. As we put more and more charge on this, electric field increases, right? This is the electric field. What will happen if you put a lot of charge? What's the first thing that will happen? We keep adding charge on, physically speaking.
You keep adding charge to the sphere.
Yeah, sphere. Let's say, yeah. Let's say literally I can come and charge on this. Let's make it abstract. And rest everything. There's nothing else in the room. Right? There's only. Think of this room, and you keep doing this. What will happen?
The charges would start repelling each other, right?
Yes, but they cannot go beyond, right? That's a metal. You cannot go beyond this. So what will happen?
I mean, once they find their point of equilibrium, nothing, right? Because there's no interaction.
In what sense equilibrium? I don't understand.
So the charges will be equally dispersed among the metal sphere itself, and then
Yes.
they will find a force dispersing as well, similar to the charge, right? So it will be even everywhere. It will be
Sure.
balanced.
Yeah, uniformly spread out on a sphere. That's good. But maybe I should give you a hint. Let us say in the room, what does it do to the room? And this is physical room, I'm saying. In this room, what will the charge do? Remember, room has molecules?
So will it polarize the molecules around it?
Polarize, very good. Yeah, polarize the molecule. Then what? Yes, good. Yeah, think along that direction. What will happen if you polarize the molecule?
It'll start to develop a face, right? Like a direction.
Yeah.
And it'll
Keep
start
going.
interacting with each other.
Yeah,
And
yeah.
then you'll find a physical field, like wave
I'm putting
of
in more
molecules
charges.
around it.
I'm putting in more charges, lots of charge. Go to the extreme. Yeah, you're right. You're thinking correct. But go to the extreme. What will happen to the polarized molecule?
So then you assume that every molecule in the room has the same charge because of the amount of charge that is being expelled from the metallic sphere. And then you would assume that they're also trying to find equilibrium within the room. They're trying to push each other away as much as possible because they all have like charges. So then you have an equal space between everything. Is that the direction you're heading for?
Yeah. That's correct. But I want the extreme. I want you guys to answer right now. Yeah, you guys.
It tracks everything, it repels everything.
Yeah. Something else can happen, maybe? It's very strong field. What do you expect? Let's say there is one atom in the room. I'll make it simple. Where do you see a lot of electric field? The largest electric field you can think of. You see it every other day.
Are you talking like the atom would split or change? Like,
Yeah, split. What do you mean by split? Yes, that's correct. Do you see atoms splitting?
Pull the electrons from
it would be in the sun. It'd be a star, but that's fusion. That's not fission.
Oh, we see it every other day. Lightning, yeah, like arc, like a static charge.
Oh, I had no idea.
Every other day when you have a static charge, you're breaking an atom. Like you break an atom every time. That's an arc, basically. If you put in a lot of charge here, these atoms close by, they will just, the word for this is breakdown. The air breaks down. Air cannot take up too much electric field. And what's the breakdown electric field for the air? Approximately. So it turns out that if you have an electric field, so you keep increasing the electric field, right? As you put in the charge, electric field keep increases. If you reach, so there's a specific number that's based on the atoms in your air, right? It's 10 raised to 4, 10,000 Newton per coulomb. It's not much. You can generate this. That's why you have static all the time, right? That's
It's like the old picture of Tesla with his.
Exactly, exactly, right? That's how, no better example than that. Yeah, that's a dramatic thing. So the question is, this is an extra credit problem, right? You have a 1 centimeter charge, you put in charge. As you put in the charge, electric field right near the sphere keeps increasing, right? Because you keep increasing the charge, 1 centimeter square. There will be a charge at which this becomes 10 raised to 4. And then the moment that happens, the atmosphere there right at the boundary will just break down and you get a spark. And it usually is a cascade. Whenever it happens, there is a cascade effect, and that's why you see an arc. So the question is, how much charge will take for you to put it on a 1 centimeter metal sphere so that this literally happens, okay? And that gives you a measure of beyond that, things are not stable. That's the way to look at it.
Could you please write the question for us to have the exact wording?
I usually discourage myself from doing that. Okay, again, in this case, I'll.
No, that's fine.
Yeah, usually why I discourage is because then you tend to think on it on your own, right? You come up with new questions. Like I might be thinking something, you will come up with another question. I want that to happen. But okay, here is in this case, let me specify, okay? There is a sphere of 1 centimeter radius, metallic sphere of 1 centimeter radius. Right? What is the maximum charge you can place on the sphere such that air around it does not break down, right? Because beyond that it will break down. It does not break down. Is that clear enough?
Very, thank you.
Right.
So the highest charge before sparks.
Before it sparks, exactly. Right. For that matter, what you should estimate is that in your hand, right, finger, like that's about, it's not a perfect metal, but assume that it's a perfect metal. Let's say it's a half a centimeter radius of that. That's why you get, and why, does it depend on the radius? Why do you get a spark all the time at the elbow or the fingers? Why not on your head?
Or point. It's the same as like a fork and spoon.
Exactly. So the smaller the radius, yeah, it's very clear, right? As you get smaller and smaller, the electric field is larger and larger. Right? So more the electric field, larger is the effect. In fact, it's a linear charge decreases because there is less charge on it, but electric field increases. So overall, that is a linear effect. Pretty like our standard introductory physics classes. We'll get. Another way to see it is now usually what I The extreme example you can think of is these days we go to the moon all the time, correct? Let's say that you have this is Earth and that's moon, and that is gravity here, right? So that's force of gravity. Let's say someone really wants to play a game, and let's say that you put a charge Q here, plus Q here, and then plus Q here, right? So that you repel this. So you want to release moon off from Earth. Right? That's one way of releasing the moon, is put a lot of charge on it, and then one would think that you need lots of charge probably. That's expected too. How much charge do you want to put? And you realize that it's not, or let's measure how much spoonful of charge. Okay, how many? So electron? No, that's not a good question. How much charge? Yeah, let's just say how much charge. How many grams of electrons? How about that? Okay. How many grams of electrons do you need to, what's the word, release them?
Repulse the moon?
Yeah, repel the moon. Yeah, repel the moon. Like simple, like what do you say? These are called armchair or back of the napkin estimates, right? Just an estimate to give you an idea of how much charge it is. So come out to be, at least if I remember right, I do this when I teach introductory physics courses, and I try to estimate this in the class. I think it comes out a spoonful of electrons. So if you take a spoonful of electrons and keep it on moon and equal charge there, then you get rid of the moon. Kind of, you don't want to do that probably. So that gives you an effect of but that amount of spoonful is probably break down the whole Earth probably, in the sense of electrically it will be screwed up. So that's too much charge. So that it gives you a feel for how much charge is. So that's why all the examples you always say micro. A supercapacitor deals with Coulomb. That's the amount of charge, but then it's very small. In a very small region, you can have that much charge, but if it is too much, then it's that's too much. Or think of supercapacitor. That's where you start reaching that millicoulomb region. Okay, so that's again going off track completely. So this is your quantity. So this is a slightly, it should raise eyebrows in a sense, or what's the word? It should surprise you all that there is some quantity that is zero everywhere, but when I add up, the integration is adding up, it gives me a finite quantity. It's non-zero value. It can give you a non-zero value. So it seems like if you pick out a point, it matters. So I think this example we talked about last time. So this is A to B, the x, f of x is equal to, let's say C is somewhere in between. So this is C, A, B, and this is x, and this is a function. Right? So this is a function f of x. That's your B, that's your C. Right? So we learned this in calculus that this is A to C, the x, f of x, plus C to D, the x, f of x. That's a theorem in calculus, right? If you're doing an integral from A to B, that's an area under this curve. The area under this curve splits into two, right? Area 1 plus area 2. That's perfectly fine. But what if you write this in the following form? So this is minus delta plus delta, and then there is a small extra piece in there, which is c minus delta, c plus delta, x f of x. And let me call that R. So this whole thing is R. And we can ask, what is R in the limit delta tends to 0 of c minus delta to c plus delta x of x, where delta is a really small quantity. So in the limit delta tends to 0, this will be c plus delta, this is c minus delta, and we are talking about this strip, the area of that strip. In that extremely small limit, when delta tends to 0, this is surely 2 times delta. Like that becomes a rectangle then. That's the width of the strip. That's the width of the strip. That's 2 times delta. And what is the height of the strip? That's the value of the function itself. That's f of c. Value of the function itself, so that's f of c. And of course, if calculus has to work, you would say that, oh, this is a finite number multiplied by some small quantity, that is 0. It's perfectly fine. But there is a small catch in here. So this is equal to limit, right? Limit delta tends to 0. And this is equal to 0 most of the time, but this is not equal to 0. Right? This is not equal to 0 if f of c were equal to 1 over delta. Because then the delta will cancel out and I can get some constant in there. So if f of c is finite. Correct? And that's what we want to define now. We want to define what is called a delta function. So we want to give some expression to this. So we want to define what is called a delta function. Right. Exactly what is this here? This is 0 everywhere, but at r equal to 0, what is it? And do something like that. So here is how, so exactly same statement, but now we are doing this in 1 dimension, and we'll come back to 3 dimensions very quick. Delta of x is going to be equal to 0 if x is not equal to 0. Okay, that's all. If x is equal to 0, it's understood that it has to be infinity, right? Otherwise, the next statement won't be true. I'm going to say the same thing. So, and integral x, delta of x, has to be equal to, now I have to integrate it from certain point to certain point. This was over a sphere of radius r, right? So here, I integrate on some any value a less than 0 and on any value b greater than 0. So I go from some value less and greater than 0, or for the matter, let me keep this open. How about this? This is a, that's b, and this is equal to 1 if x is less than b, oh sorry, 0, right? 0 is less than b and greater than a. This is equal to 0 all other times if 0 is less than a, b, right? Both are greater than 0. It is also 0 if both a and b are less than 0. And we will avoid the scenario when this a and b is exactly on x. Then there is an ambiguity there. So we'll just avoid that whole. So that's the requirement. This is just saying that for any quantity. Another easiest thing is to say that it's minus infinity to plus infinity, that is equal to 1. Right? Very similar to this. It's the same idea. That's going to be our delta function. And it's surely a very, like if you want to visualize this, this is your, so usually we visualize a sine function as a function of x. So this is your x. And if I were to plot f of f and your delta function, so it's 0 everywhere except at one point. Right? It goes all the way to, and it has to be infinity because otherwise, like x equal to 0, it must be some kind of infinity because only then the integral can be a finite quantity. Okay. Any questions on this up to now? Okay. Okay, so representation of representations. So there are different representations for delta function. So just to have a visual feel for it. So representation 1, let's say there are many representations of delta functions. The easiest is the visual representation is, let's say f of x is equal to, think of this as your function x, and let's say this is height, this is width, let's say w, right here, w is a width, but the height of this function is actually the inverse of the width. Right? So then, and we want to take a limit w tends to 0. So this is equal to 1 over w if x is less than w over 2 and minus w over 2 and 0 otherwise. And delta function is equal to limit w tend to 0 of f of x. We have to satisfy these two conditions for delta function. So we immediately see what is at x equal to x at x not equal to 0. What is it? So of course delta of x is x not equal to 0. So since that is just 1 over w times w feature no at x not equal to 0. At x not equal to 0, so we are outside this, but we are taking the limit w tends to 0, so this is equal to 0. So you have to see it graphically. Like, there's not much you can visualize in there. And integral of dx delta of x, and let's do minus infinity to plus infinity. Right? That's the easiest one you can do. And again, graphically, right? So this is the area under this curve, how much ever you go. So this is actually equal to 1. Like again, graphically, it works. Another representation which is more useful, or useful means it's more algebraic. This was very visual in a sense, helps representation 2. And for that, let's say f of x is epsilon over x squared plus epsilon squared. And there's an epsilon here, so I'll define my delta function to be limit epsilon tends to 0. So epsilon is, yeah, it doesn't matter whether it's 0 or negative. And this is f of x, right? Take the limit. Let's
Did he disconnect?
I believe so.
That's insane. I thought it was my internet. I'm like, oh, my internet's gone. Damn.
Yeah,
And
I
then-
literally just checked mine too.
I don't know how to tell him.
Well, it looks like we got a class 10 minutes early.
That's not good because he's given 10 minutes more of a lecture than we need.
I know, it's at least on YouTube.
No, it's not because he just disconnected. It's recording this.
Oh, you're right. Okay. I don't know. It's not like you
Well,
can answer an email.
Yeah. All right. Well, crap. I guess give him a chance to notice that it's not streaming on his computer anymore because he at least had it up on the screen, right?
Yeah, I think so. I don't know.
I think they're smart enough to realize that they don't see our names anymore.
I hope so.
He's going to use the last 10 minutes just trying to reconnect. So, yeah. Damn.